Okay, good afternoon, everyone. Welcome to TAMIDS speaker series. I'm Senior Ye. I'm a professor of the Department of Landscape Architecture and Urban Planning, Geography, and Multidisciplinary Engineering. I direct the Center for Geospatial Sciences Application and Technology, and also the founding director of Urban AI Lab through Texas A&M Data Science Institute. So today, our speaker, Dr. Bhaduri, is a corporate research fellow and the director of the Geospatial Science and Human Security Division at the Operation National Lab, where he is responsible for a research portfolio focusing on novel implementation of geospatial science and technology across energy, environment, and national security missions across the U.S. government agencies, including the Department of Energy, the Department of Defense, and the Department of Homeland Security. Dr. Bhaduri is a fellow of the American Association for the Development of Science, the American Association of Geographers, and currently he served on the Geographical Science Committee for the National Academy of Science. He is a leading scholar in geographical information science. At the same time, he helped fund the U.S. Department of Energy's Geospatial Sciences Steering Committee, and it helped produce many next generation workforce and to serve the nation and the world. Without further ado, I will welcome Bhaduri, and his talk is geography mapping and energy, national energy missions and Operation National Lab experience. Welcome.
Thank you, Shenry. Thank you. Thank you very much. That description is much better than what I am. Okay? You have to trust me on that one. Okay. Can everybody hear me okay?
Yes.
Can somebody do a check that people online can hear me okay? Because I like to move around. Good? Okay, all right. So first of all, welcome to this seminar series. I am intimidated that when I found out that I am following Mike Goodchild, who was the first one on the series, and then Shenry asked me to do it. It's a big shoe to fill. So don't be too disappointed after listening to me if you have heard Mike speak. This is my first time in College Station, Texas. Although I started my academic journey in Richardson, Texas at UT Dallas. I was there only for a year, so I didn't spend a lot of time. But I have made my pilgrimage to North Gate last night. So I know what the bars look like, which is the most important thing you want to know when you're a student at any university. Okay? That's what fuels innovation. So in my first year at Dallas, at UT Dallas, I guess what I learned the very beginning. Anybody wants to take a guess? What did they teach university students in Dallas when they arrived, especially from another country? If you do not know, I will tell you, okay? It was all the Aggie jokes. Are you familiar with the Aggie jokes? Okay, I'll just tell you one because we don't have as much time. Two Aggies going to Houston, okay? And they say bye to their friends. They leave to go to Houston, and then in an hour they're back. And the friend said, "What happened?" Said, "Well, we were driving fine, but then there was a sign that said Houston left." Did that make any impact? No? All right, so here's what I'm going to do. I am going to talk a little bit about what Oak Ridge National Laboratory is, because I am going to assume that you do not really know a lot about the National Laboratory System, although Texas A&M is part of a management organization that manages one of the big national laboratories, right? I'll talk a little bit about Oak Ridge and how we got to this, and then give you examples of some of the work that we are doing that touches geography, data science, and we support the federal mission, right? So it's a very mission-driven space. And hopefully at the end, give you some examples and inspiration about why we do what we do and how it is different. Okay, so how many people have seen Oppenheimer? You should all know about Oppenheimer because Texas A&M actually now is one of the entities that manages Los Alamos, right? So it's very important that you know that Oppenheimer. So the three labs that came out that made the Manhattan Project successful was Oak Ridge, Los Alamos, and Hanford in Washington. So the Clinton vial, which is the graphite reactor, that's where the experiment was done to enrich plutonium from uranium. Okay. U-236 was processed. Then it was mass produced in Hanford, and it was assembled to create the weapon in Los Alamos. So I took my first office at Oak Ridge was about, there are plenty of seats out here, although I'm scary enough that everybody wants to sit at the back. So I started my career about 200 yards from this building, and it took me 9 years to actually go and see it inside. It's a fantastic, it's now part of a national park system. It's called Manhattan Project National Park, which the three labs are part of. And that's actually now an open display. You can go inside and see it. It's an organized tour. So that's how we came. But the use of geography and GIS and data was not accidental, right? So these are the three maps that show that how these three sites were actually selected and created these maps based upon the research. So today it's a middle school exercise of site selection using a GIS. In 1942, it wasn't quite that simple to create these maps. So mapping has long been associated with the DOE and our energy mission. Today, we have 17 national labs that are all part of the Department of Energy umbrella. And they are kind of broken out into supporting four different missions of Department of Energy: science, energy, national security, environment. So these are all the science labs. So Oak Ridge is the largest multi-purpose science lab, and we follow. There are plenty of seats up front. Where we do anything from physics to neutron sciences, to environmental science, chemical sciences, you name it, nuclear engineering. So these are the lab that support science. Here are the four energy labs. National Energy Technology Lab, which is what we call the fossil fuel lab. Idaho National Lab, there's the Nuclear Energy Lab, and National Renewable Energy Lab in Golden, Colorado. That's about renewable energy and energy efficiency. And then there are three large national security labs. These are the nuclear weapons labs: Los Alamos, Sandia, and Lawrence Livermore in California. So that's where a lot of the weapons mission is done. And the latest in the family is a Savannah River National Lab, which is the environmental management lab. So that's where a lot of research is done about nuclear materials out in the environment. How do you monitor it? How do you clean it up? And how do you make a difference? So it looks very much like College Station. That was the other Abbey joke. It does not. Okay. It looks, so we are part of a 44,000 acre campus, most of which looks this way. Most of our interns get a shock of their life when they realize that, so we are housed in this building, and from the last traffic light, it's about 6 miles before you get to that building, okay? So there is fear of getting lost almost, but it's a very large campus. So at Oak Ridge, we support what we call discovery science, which is on the left, which are neutrons, computing, materials, fission and fusion. And on the applied side, where we are developing applied solutions for energy transitions, biology environments, isotopes, and national security. Isotopes is an interesting aspect. Oak Ridge, we produce 30% of the world's radioisotopes that are used for medical treatments. Okay? The entire field of radiation therapy for cancer came out of the Manhattan Project because that's where the nuclear radiation was measured on mice. So it's a very significant. That's where it was discovered that the Y chromosome actually dictates your gender on mice. So there are lots of firsts. And our division sits under the National Security Sciences Research Directorate. So we are about a research organization that has about 100 researchers. And we are all focused in moving the needle in one of these areas, which is high performance geocomputation, human dynamics modeling and simulation, critical infrastructure resilience, remote sensing and autonomous systems, and then AI for mapping and monitoring. This is where we are heavily focused. But what we produce is our data, analytics, and then subject matter expertise that the federal government relies on us to help them and guide them in terms of future investments and decisions. So those things touch the human landscape, the built landscape, the physical landscape, and then also the information landscape. And what I intend to do is to walk you through a series of examples that will touch some of these areas. So what is the difference that we are trying to make? Okay, what is the difference that we are trying to make? One objective is to reduce the latency of data generation and delivery. How fast can you do data generation and how can you move it? So that's where the automation and augmentation and large machines come in. The second one is, can you create high resolution, high unique value data resources that nobody else will try to create? Because it requires very large scale infrastructures. So high resolution in space and time at global scale and as accurate as you can get them. The third one is we support mission analysts with scalable analytics. So this is where we produce real tools that gets used by people for decision making every day. Okay. And the last one is a key aspects that we do across the national labs, which is we de-risk and accelerated government adoptions of novel technologies, right? So the one that we are working on right now is how to de-risk the small satellite industry because they are not stable, okay? There are too many of them. They're producing too much data that is unusable, okay? For the government to use, you need to de-risk them by creating some technology solutions that can one of them. I'm not going to be talking about that, but if you're interested in that area, I'll be happy to talk to you afterwards. So to give you examples of this unique data resources, one thing that we are known globally for is creating very high resolution population data. Okay. And so we have been doing this for the entire global community for the last 35 years, 25 years. We have a global data set at roughly kilometer resolution that we update every year. We have a US data set that's 90-meter resolution, but that's both nighttime and daytime. So it's a first ever time variant population model. And right now we are scaling that US data for the rest of the world. So we will, at the end of FY25, we will be coming up with a 90-meter population data for the whole world. And as you can see, as this thing loops back in, the dynamics is a variety of scales from seconds to minutes to decadal scale. Population dynamics is what we are interested in. But I want you to follow the diurnal variation of Washington, DC. The reason that is important is you might be thinking that you are looking at a population data. How does the population vary in a 24-hour cycle? We're actually looking at your energy demand now. Okay? Movement of people drives every infrastructure, including energy. So that's why knowing where people are is very important. So the question is, how do you do it? And this is the highest level representation of how we do this magic, right? So the US government spends $300 million a year buying commercial satellite imagery that are about 50 centimeters or higher. We extract settlements and buildings for those satellite images because that's the biggest indicator of human presence. Okay? No buildings grow in nature. If there is a building, some humans have already been there. From those settlements, we create a second order data product called the neighborhoods. And I will get into a little bit of the neighborhoods. These are contiguous, uniform formalities that define a particular area based upon these structures. Then for every neighborhood, we are looking for 3 different types of information. Can we tell how tall these buildings are? Can we tell what these buildings are used for? And then do we have any idea about how many people in that area, some level of density, people per area, okay? And then you can create these high resolution maps. Now, what I just simplified, this whole thing, every bubble here is an independent project by itself, okay? So a PI for every bubble can come here and spend an hour taking you deep down into how that thing is achieved. So this is about 30 people, about $6-7 million of per year effort that goes from left to right. So it's a pretty large effort for data production. Now, why is it that we are interested in buildings, and why is it's a challenge? Okay. So 2% of the global surface is occupied by buildings. Okay. You can think of the challenge in another way, which is if you take the 8 billion people of the world and you make a unit family of 4, which is the standard accepted definition of a family, father, mother, and 2 kids, a boy and a girl, and you give each family 1/4 of an acre. Okay? 1/4 of an acre is a fairly decent, real estate for most people in this world. You can fit everybody in the world in Alaska and we'll still have 10,000 square miles left. So the challenge is the people are distributed, okay? So here is a couple of examples, which is from the global south. Mali has only 0.02% of its surface that is occupied by a structure. And Venezuela has only 0.13% of its surface occupied by a structure. So this is truly a needle in a haystack problem, right? Especially when you go outside the cities. The urban areas are easy. So for the last 15 plus years, we have been trying to do 2 things. One is improve the algorithm that will give you better detection of buildings and mapping of buildings. And of course, deep learning and CNNs have given us that edge. The second thing was the technology, okay? So since we house the largest machines in this world, we work very closely with the chip manufacturers, for example, NVIDIA. And so we work with them closely on the chip and what you can run on those chips. And we found that GPUs change the game quite a bit, right? So if we think about benchmarks, 3,200 GPUs on Summit, which is now the number 5 machine, we can map every building in Iraq in 4 minutes. Okay. So reducing the latency is really relying on good algorithms and fast compute. So being the most advanced Western country, debatably, in the world, the US did not have a whole comprehensive buildings data set. So we were asked to produce one. So we processed about 1.2 petabytes of data and produced it twice. First from an imagery source that USDA has called the NAIP, National Agricultural Imagery Program. And that is 1 meter in resolution, and but it's consistent imagery, so it was a generalized model that mapped some buildings. Then we repeated the same process on commercial high resolution, which is 50 centimeters or less, and mapped about 125 million buildings that are 450 square feet or larger. Okay. Somebody asked me this question, why did you come up with 450 square feet? I'm assuming you are all asking me that question in your mind, right? This is a shy crowd. 450 square feet is the size of a mobile home park. Okay? The trailer homes, that's the size. And FEMA's first requirement was, can you tell us where all these trailer homes are? Because those are the ones that get impacted the most anytime that disaster happens. They get washed away, blown away. So that was the target. So I will come back to these data sets at the end. So I was just discussing this, that we have a very ambitious effort right now called the Global Buildings Intelligence. And what we are trying to achieve is map every building on the planet and then know something about that building as it exists. How tall is the building? When was it created? When was it built? How many people live, use it? How many floors are there? What is it used for? What material is it made of? Everything is there. So we are creating this Bayesian network that is allowing us to build this attribution for these buildings very, very effectively. And I will not get into the details of this, but we have run some prototypes and pilots in Knoxville where we are, so we can do some validation, and the results are very, very promising. So what do people do with this buildings data set that FEMA has used, right? So every time there is a disaster, FEMA is using our buildings data sets, the ones that we produce for them, in information and map products for understanding what the impact, where the impact is, and then how do you solve some of these issues. Okay, so I talked about buildings, let me talk about neighborhoods. So this is Caracas, Venezuela. Okay, this is a half-meter resolution satellite imagery collection of Caracas, Venezuela. This is what it looks like when you map all the buildings. Okay. And then when you apply the neighborhood statistics, this is what you get. So every color is a different kinds of neighborhoods or compositions in terms of form and formalities. That's what it's essentially showing you. Now you have to ground truth this one way or the other, and there are many ways you can do it, including local knowledge. But that's not the point. The reason we are interested in this is because the formalities of settlements indicates few different key things that we want to know. One is how resilient are these structures? So if there is an earthquake, how much is going to stand versus how much is going to crumble? Okay. The formal buildings are energy efficient, more energy efficient, but they consume a lot more energy than the informal ones, which are less energy efficient. Okay. So you can get an assessment of your energy efficiency and where you need to increase resiliency from these kinds of data sets. So this is very, very novel and exciting as we are going. So I had a PhD student a while back who looked at, can you look at these neighborhood data sets and the famous nighttime lights data to see whether the formality has a correlation with intensity of electricity or intensity of this light or the electricity? And the answer was probably. So of the three cities that he looked at, the signals went from, the R square was from 0.44 in Johannesburg to pretty high in Angola. So maybe. Not sure, but could be. Okay, so we can map a lot of things using this AI and using computer vision and AI at scale. So we did this for solar panels for DOE, and then it was scaled by a group at Stanford. If you're wondering what's the what's the point of mapping solar panels on buildings, right? Who has solar panels is the biggest hurdle for market penetration for the installers, because they don't know who has it and who doesn't. Because for all you know, you're going to put the solar panel on the other side of the road, right? Then you do not know. And if you don't know who doesn't have it, you cannot go market and do it. So it's very interesting to know that how you use that information and data to understand who has it, who is more likely to have it. Because if you see all your, we all do follow the Joneses model, right? The more we see people around us adopting our technology, the more we feel that we might want to jump on that bandwagon. And the second thing that they wanted us to do is, once we knew where these solar panels were, they wanted to know what kind of demographics are covered by these buildings, okay? Who lives there. So if there's a particular demographic group that is really taking it on, you want to push that everywhere else in terms of marketing, so the adaptation goes much faster, right? This is nothing new. If you go to business school, they will roll their eyes and say, how do you think we market all our products, right? That's how exactly they do it. Every billboard that you see, there are a few PhDs who come up with this placement of a billboard on a thing, and they want to know who's your audience, are you going to, meet with them or not? So this was an interesting one. Water is, of course, a very important one, and one of our staff members wanted to know, can you scale a water detection algorithm? And it turned out that this machine, Titan, which was 10 years back probably, was the fastest machine in the world, with our 10,000 nodes, Taylor mapped every water body in the state of Texas in 10 minutes. Okay, and then he also came up with the NDWI that gives you a sense about how dirty your swimming pool is. Okay, so if you see your house in here, we know how dirty your swimming pool is. But this is, CDC was very interested in this one because they want to know the stagnancy of these water bodies, because that's where the mosquitoes start spawning. Okay, so in Puerto Rico, in Las Vegas, those became a really important one. So mapping water is a very important aspect. But we have been able to make some very cool applications of this. These are about mapping mass graves. There are people in the federal mission who actually look at data, like at Ukraine and Russia, and they try to find these mass graves and try to count and try to understand how many people are dying. Okay? These are genocides. And these graves, if you rely on human vision, it's not scalable, because it's too long, too wide of an area to find these, and they change back to the background vegetation in a matter of days. Okay? So this was a very powerful, and then what these means is the manual count versus predicted, because everybody will ask, how good are your algorithms, right? So, and everybody believes that another human is much better, which is not true. But at least we saw that if you let a human analyst count the graves versus you let the machine count the graves, they get pretty good agreement. And here is another example, so you can kind of see where the graves are, and then the manual versus the algorithm. So this is, I talked about the big machines, what we are doing with the very large machines, right? This is on the other end, which is on the edge. So this is edge AI. So we trained a model that knows how to identify utility poles. Okay, utility poles that you see. So every time there's a disaster, especially hurricanes, everybody says, give me a satellite image. And they do get a satellite image of beautiful clouds. Because after hurricane, there are just clouds, right? So all your utility companies are waiting outside that area, waiting for the wind to drop below 20 miles an hour in their trucks, and then they will go out, drive, and see what's up, what's down, what is damaged, what is flooded, and then they will bring back that information and make a plan for infrastructure restoration. Okay? The number one thing people are expecting to be back after any disaster is electricity. You don't get electricity back, you cannot get anything back. So this is absolutely foundational, fundamental, life-changing exercise, right? So we are working with DOE ESF 12 and Emergency Support Function 12. And what we have done, we have a group called Autonomous Systems. They make these custom payloads. So they have these cameras mounted on these drones. And what the drones do is as they're flying, they automatically detect these poles, and then they give a signal. Pole is intact, pole is damaged, or I cannot tell. Okay? And based upon that, because remember, there is no cell phones, right? You cannot push images and videos back to and it's useless. So what they do, they have a comms chip in there that pushes that data in real time through satellite communications back to these people who can immediately start planning that what is done. The other challenge of driving the truck is all the roads are full of debris. So you have to wait for hours for people to come and clean the debris so you can take the truck in, right? So this is absolutely game changing. So this goes back to that thing I was talking about, that how do you reduce the latency of data generation to delivery? So we also use a phrase called data to decisions. And this is another example of that. Okay, I'm going to talk about another favorite thing that is going on. High resolution elevation models at scale, okay? The whole global community relies on one elevation data, SRTM, shuttle radar topographic mission. Do any of you know how long it took to do the SRTM? 12 years. Okay. Because it's an active remote sensing. So a team from our end, what they realized is that we have been paying the commercial vendors, the digital globes and the Maxars, and for years collecting all these data, $300 million worth of imagery, right? So if you take those and you use a machine learning algorithm to find the optimal pairs that are within 40 degrees overlap, you can generate a stereoscopic view and you can train that algorithm to generate the point clouds and so on, and create a digital terrain model. Okay. And so that's what we did. So watch carefully here, okay? Can somebody get the light from the back, because otherwise the magic won't look as good. The one. Yeah, that's a back one. Yeah, let the back one. Yeah, turn the back. Yeah, perfect. Okay, this is great. All right, so the background is SRTM. And when I click, you will see the data that is generated from fortuitous studio pairs with point clouds. And that is at 1 to 2 meter resolution. Okay? But since you are generating these from the archive, the other thing that we are being able to do is to use a large machine to process it very, very fast. So with a old algorithm customized for GPUs, and then designing a chipset that allows really efficient processing of that data, the imagery. So with that kind of a speed, the benchmark is that now we can produce a global surface terrain model every 90 days. Okay? So from 12 years, we can go down to 90 days and probably faster if we expand that cluster. So that's a big success. Scalable analytics, this is what I would say distinguishes the national labs. We created a sort of a fledgling capability for wide area visualization after the 2003 big blackout that happened in the US Northeast, and 45 million people were left without electricity. So today we have this capability called Eagle Eye, Environment for Analysis of Geolocated Energy Information. And what that basically is that every 15 minutes, it tells decision makers how many people in any county in the US do not have electricity. Okay. And that runs 24/7, 365 at Oak Ridge. And it's used all the way from DOE headquarters to the White House Situation Room. Okay. So there's a very little margin of error that you can use. It is actually a phenomenon. So about 93% coverage of the US territories in terms of customers, because there are so small utilities that are out there, it's almost impossible to get their real-time data from their websites. So this is what it looks like. There is 1,000 users across the federal agencies that use it every day to understand what is going on with the power situation. And of course, Texas is I didn't make this up. Texas is our favorite because it just, from Uri to Katrina to, Texas always attracts. And then these are the data sets. And this is what goes for presidential disaster declarations, right? This is real time as it goes. We have another capability for collecting what I call the digital exhaust, the social media, the publicly available and commercially available information. We collect these points of interest data, and this statistics is kind of old, but we are given these campaigns for particular events that might be happening, right? So let's say election in Turkey. And then we would be asked to collect data around Turkey. And that is done at a pretty astronomical speed. So about 3,000 records per second and 3 gigabytes of imagery per day. So it's fairly robust. But what do we do with it? You remember we talked about nighttime and daytime population, right? So here is something that we call the occupancy curves. And on the very right, this is retail space, shopping malls, and country A, country B, and country C. Who wants to guess country C? How many geography students are here? That is Spain, because you see the siesta, right? Middle of the day, people are not there, okay? So you can do this at a global scale. So this is one utility across country. This is global scale, schools, museums, and restaurants. And so it has given us opportunities to understand across the world, behavior of people and usage of spaces, similar spaces, using these kinds of data sets. But the best utility of this is where we are really happy is, remember I was talking about the daytime and nighttime population data? But somebody in a meeting, somebody very important in a meeting said, what does daytime mean? What is it? What do you mean by daytime? Is it when day breaks? Is it when sun rises? What is it? So if you think about these semantics that we use, like afternoon, evening, there is no finite bound, right? So what we ended up doing is the most consistent way of defining those terms is to do it by socioeconomic signatures. Okay? If people are out at the malls and eating at restaurants, it is evening. It might be 9 p.m. in Doha, Qatar, or 10 p.m. in Doha, Qatar, is because it's damn hard to be out there before that, right? But it is evening there, okay? A lot of the European countries, if you go, nobody goes to the restaurant starting before 8 o'clock. It doesn't even start seeing light, right? Here, people will be starving by 8 o'clock, okay? So the socioeconomic signatures are a very good way of understanding this concept of time. Here is another system that we have built for one of our sponsors called World STAMP, World Spatial Temporal Analysis Project, and I described it as this is the largest socioeconomic data cube that the US government has ever produced. It is at a country scale. It has about 60 years, 16 million records, 14,000 attributes, but you can do some cool things with it, which is space-time analytics and visualization, right? So these are not choropath maps, which are very intuitive for geographers and cartographers and the common person, right? That you feel like the color represents one value. But what this really is, these are trends, okay? So let me give you this example. This is a global scale. So in the system, you can go and select between 1990 and 2015 CO2 emissions. And you tell the system that bring me the top 6 trends in the world. Okay? Out of the 196 countries, give me the top 6 trends. So it figures out what the top 6 trends are, and then color codes the countries based upon those trends. So now all of a sudden you can see that there are these apparent anomalies that are going on, that their CO2 trends are not, doesn't belong, although they are geographically contiguous, their trends are not, right? So it lets you ask more questions, saying why not? So this is data driving hypothesis generation, right? You're just asking the data to tell you patterns and you're generating questions for that. It's very powerful. Okay, since this is a very urban design, urban focused crowd, I could not resist to talk about the most favorite project I've done in my recent life. So the city of Knoxville, they have LiDAR data for the entire city, okay? The entire county. So about 10 years or so back, they said, you know, can you take that data and tell us how much electricity can be produced if we put solar panels on every city or county-owned government building? That's a fair question. So what we did is we came up with this kind of a thing saying, you know, this is in a day in July. As the sun moves, you can see how much reflect or radiance of sun you have on that landscape, right? By the way, do you notice the place of worship? I visited yours today at lunch, or at least drove by it, okay? That's the place of worship. Chenwei was trying to tell me that's the stadium, and I said, you will get killed if you said in Knoxville, that's this Neyland Stadium. That's a place of worship. You go to church on Sunday mornings and you go there on Saturdays before that. So we did that thing, but then we were working with the city and we found out that the city has $178,000 in its annual budget for treating winter weather in Knoxville. Okay. Now I know that you guys could care less about winter weather, but bear with me. Okay. So what that meant is that, you know, there are about 2 to 2.5 of snow or ice event they can manage. And then they will have to beg, borrow from everywhere. 90% of the US counties which gets winter weather or snow and ice events break their county budget backbone from dealing with it. 90% of them. It gets variety of kinds, like New York City has to bring in trucks to haul snow out because you cannot dump it in the river. DC does the same. So greater DC has 200 salt or brine trucks. Knoxville has 23. Atlanta has 2. How many does College Station have? Yeah. Okay, makes sense. But what I was intrigued that the engineering was fascinating. It's a truck that you load your brine or your salt and the driver starts driving and the valves open and they spread this salt and brine. And then if he stops with the brake, the valves close, okay? So I was intrigued, saying, why do I want to do this? I have all these fantastic data that shows me the terrain, that I have the LiDAR for the trees, the building. So we came up with what we call a risk map. That means what parts of the road naturally get a lot of sunlight, that the snow and ice will melt automatically as opposed to that are shaded, right? So that's what you're seeing there. But then I worked with the University of Tennessee. I want to watch it and I'll talk you through a group of kids in a marketing class. They took our lab prototype and in $1,500 produced a field prototype. And now the city and the county each have one of these trucks that are empowered with this risk map, GPS. Of course they have GPS. And there are these 4 different spread rates. So for every quarter of a mile, it knows from the map what kind of risk level it is, and it regulates that flow. So salt and brine is the #1 corrosive agent that is governing the environment. It's the #1 cause for fish. Water increase and ecological trends, ecological strength, all hit. So we are minimizing cost. And then if we think about loss of property, and because you are, you will get a lot of, slope. That's your high risk, right? So it's savings everywhere. And simple geographic data sets can drive these kinds of local innovations. So let me talk about one thing that we as a national level employees will have to do, which is when there is a crisis and the government comes and says, we need help, we have no opportunity to say no. Okay? Or there is no student who's working on this right now. So COVID was one and Ukraine is another one right now. So we are applying this all the time, trying to understand building damages in Ukraine. And once the building damage we can get, and it's a pretty heavy turnaround, right? So a lot of times our teams will work through the weekend. So they will work from Friday all the way through Sunday to produce these kinds of outputs. And then that will go into, understanding displaced population, how many people can go, and then update the population data in as quickly as possible. Here's the other thing that we did. The State Department was working with the Conflict Observatory at Yale University and mapping every silo, grain silo in Ukraine, because that's a big sensitive component, right? Ukraine economy relies on the grains, and the Russians were taking the grain silos away, not like destroying. They were just moving them and shipping them away. So that was the thing, and the president last September of 2022 gave a talk at the UN on food security, where he was going to make this, that's fund the project. So few of my staff members were volunteering for this project on weekends. And at one point they realized that there is no way Conflict Observatory could scale the AI algorithm for grain silos using Google Earth and the rudimentary infrastructure they had. So we got involved and we mapped all the grain silos, and it's a public report on the Department of State website that we had to jump in and make sure that that was successful, because the president was going to do a speech with that data. Use to nighttime lights to understand infrastructure changes, like whether electricity is coming back in Europe or not. And we help GOE understand what is going on. So I'm going to tell you like what makes it worth it. Okay. So one of the things, and I'm doing a sales pitch here to inspire all of you to think about coming to Oak Ridge at some point. So a few months back, I was talking to a group of new employees, and one of them asked, like, well, it looks like you have never gone anywhere. You have been here for 25 years. So what is it that's so good that you didn't think about leaving? And I was not quite ready for that question. So I made up an answer that I knew was not quite good, you know. But then I kept thinking that, you know, what is it that makes you think that this is a good place to be? So I went back to her with these examples. Remember I talked about the buildings data set, and I talked about the mobile home parks. So one morning, as Hurricane Matthew was about to make landfall, we got a call from FEMA response, and they said, we need to produce these maps with the locations of these mobile home parks, and also where we can put FEMA shelters, okay? So these are standard cartographic products. So here is another one. And the next morning, I got an email from the FEMA point of contact saying, you guys did good. Okay. This is what makes it worth it. So I have not one, but two examples of our research and development and our products in the hands of decision makers at the highest level. Okay. That is powerful and impactful. You feel inspired and motivated to do this. Okay. Now, for all you inspired academics, including Shinwei, I will challenge him to one day, I want him to bring me a picture where instead of this being a map, the president is reading his IJGIS paper. That's a thing out there. All right, so, you know, I have this very nice job. I go around and I tell people these stories, and it makes it sound like I'm doing everything. I'm not. I'm an expert of two things: Outlook and PowerPoint. That's what my expertise is. But you know, I have an organization of 100 people, 100 staff members. It is an incredible amount of work that's going on across the board. We have tons of students who come and work with us, a lot of in the summer and then during other times too. I almost put in the picture of the group from 2005, which had Tony Philippi as a freshly minted academic at University of Kansas, who's now a faculty of geography here. So Tony spends 2 summers with us. All right, so I'm going to stop there. And I have 6 minutes left for questions.